So hello everyone. Let's discuss linear transformation. So linear transformation, we need to talk about. So for linear transformation, we need to talk about functions a little bit. So what's a function? Yes. So what's a function? When you see mathematically, a function is a mapping from one set to the other. But we have some constraints attached to that mapping too. Okay. Now you know the constraints. For example, the first set should be non-empty when we map it to the second set, and there are other concepts too, which I'm not going to do, not going towards that. But basically, let's see the definition only of what's a function, and let's try to associate it with the linear algebra. So if we have a function f that goes from set x to y, then in that case we can say the expression f such that x goes to y is a notation for function, and the range and the domain are given as the range of f is given by range of f is equals to f of x such that belongs to x belongs to x. Okay, so this is the range. This is the way how we represent range. Is it visible? I think so. Yeah. So this is the range, and if you want to write the expression for domain, you can write domain of f is x such that x belongs to x. So we can write that, right? Yes, we can write that, but it's so trivial. We don't write anything about domain. But it is this notation is important of range. Okay. Now, if you want to say this to be function, and let's suppose the inverse of this function exists, what do you remember to be the criteria for the function to be inverse? So, right, function to have its inverse. So the criteria, if you not remember, they are it must be onto one, onto onto function. It must be onto function, and it must be one to one function. Somebody of you might be familiar with the words injective and surjective. When a function is both surjective as well as injective, then it is said to be a bijective function, and such bijective function has an inverse. That means the inverse exists for such kind of functions. Okay. So here we have an example. For x in the interval from 0 to pi, define f of x equals sin x. Find the domain, codomain, and range of x. So we have a function which is f of x equals sin x, and we have to find out range, domain, and codomain. So we have to find out range, codomain, and domain of this function, where the domain exists from 0 to pi. Okay, yeah, so this is our domain interval. Okay, this is where the function exists. If you want to see it visually, you can think of it as a sine function going from 0 to pi. Alright, it's pi by 2, so it's pi, it becomes 2 pi, that means we are just bounded to this pi. So we have got these, and we know sine, the value of sine goes from 0 to 1. So this is what we assume the range must be within, that is from 0 to 1. Okay, we can say this is an interval of range, and we have this function. So if you want to write the range of f is equals to f of x such that f of x, what was it, f of x such that x belongs to x is equal to close interval of 0 and 1. Now what do you think the codomain is? Codomain means the set that includes the range and may include other terms too. Okay, whenever we imagine function as f of x to y, then we can imagine codomain to be the full y set, and among them, which are the elements of y which are mapped to x are said to be in the range set, but the ones which are left without mapping, then they comes into the codomain alongside with the range. Okay, so these are, now we know there are no points left if we map 0 pi to 0 pi to 0 to 1, because if you see f of x, when f is 0, sine is also 0, so this is the interval, so we don't have anything left in the upper side. If you see the lower side, f of pi becomes sine of pi equals 1, then again we don't have anything lower than that boundary in our range. Yeah, so so this is what we found to be the codomain. Now codomain in this case is equal to range, so we don't have anything which is obstructing us to write codomain is equals to range. So we can say codomain also has the value 0 to 1. Okay, I think I made it sound very complex, but it is not so complex. You know that. You have to know these things because these are very elementary. Now let's see transformation. What is transformation? Before going to the actual definition of these, let's take an example of transformation. Let's suppose we have a transformation. Now I haven't even discussed what a transformation is, so it doesn't matter if you don't know how to do this question, but I'm going to write this question. Okay, so we have a transformation from R2 to R3. We are mapping defined by transformation of x is equals to ax, where A is a 3 by 2 matrix which consists of elements 3, 1, 2, 5, 7 and minus 2, and U is something which is defined as 3, 1 and 3, and V is 3, 1. Now we have to find out the transformation of U, transformation of V, transformation U plus transformation V. Okay, to find out. So these are to find out. Now we have given all these. So what do you think we should do here? I think you are very familiar to this and you won't find it very interesting because it's obvious. So we have this transformation, okay? So this is a function, we can say, of x so even so before thinking of this is a transformation, just let's think this t is actually a function which goes from set of second dimension to the set of third dimension, which maps the second dimension to the third dimension, and we'll see what that means later on. So that has a matrix, and that has some things there, u and b, defined as u and b, and the formula or the mapping, yes, the function is t of x equals ax. Okay, now we have to find out tu. So I think you can do this. X equals u becomes tu equals a is 3125 7 minus 2 and u is 13. That's so we have to find a multiplication. Now for every matrix multiplication, it's 3 into 2, it's 2 into 1, so it's compatible. So we are gonna have a 3 into 1, 1, 2, 3, 1. We can say a vector in 3 dimensions, which is gonna be what? This times this would be 3 into 1 plus 1 into 3 is gonna be 6. This times this is 2 1s are 2. 2 times 1 is 2 plus 5 times 3 is 15. It gives us 17. 7 times 1 is 7 minus 2 times 3 is 6, so it gives us 1. I think I'm correct, okay? Now similarly you can find out TV and you can add these two to find TU plus TV. I'm not going to do that, but I'm going to do something else. So you have just seen that this t of x, the function which is t, the function t defines this function. What do you think it just did? It mapped second dimension to the third dimension. You may say, how? If you see x, how many components are there? Now we have assumed x to be u, so how many components are there? 2. How many components does the result have? 3. That means if we have R2 to be our set, we can think of it as a set, and we have R3, so these are mapped. Okay. Now if you remember the last video, we have defined an analogy of set in vectors too, and the analogy was, we can think of actually, and it is a fact that we can think of the set in linear algebra as vector spaces. So we can say that this and this are actually two vector spaces. If you write generally as f of xy, we can think of these two as different set of vector spaces. Okay. Now in that vector spaces, we have done a transformation. Now why am I repeating this word? Why I am saying this is a transformation? I'm saying this, you can think of it by just the literal meaning of transformation. I am transforming the second dimension to the third dimension, but alongside with that, or in addition to that, I'm saying this to be transformation because we have a matrix involved, this, and actually everything here, the whole picture is actually on the basis of this A. If we had different A, then we would have different result. Okay, and that would determine what is the mapping or what is the set. Another set of mapping would be. That's why everything depends on this A, and this A has a name, so it is called transformation matrix. So you can think of transformation matrix, okay, or sometimes called as a matrix transformation, because matrix is involved for transformation. Transformation of what? Transformation by using a function which involves the transformation matrix of different vectors. Okay, I think that makes sense. Now I have just defined two things which were injective and surjective. So let's go deeper and understand what that means in our scenario. So injective means if we have a function that goes from x to y, then it basically means one to one. That means all the elements of set x maps to all the elements of other set. So none of those elements in either of the set remains unmapped. This is what the meaning of injective is. Okay, that means if you see mathematically, then let's suppose we have u and v, and these belongs to the domain where u is not equals to v, then f of u will not belong to f of v, will not be equal to f of v. Equivalently, if u is equals to v, f of u will be equal to f of v. It means that if we don't have the equal number of u and v, then it would be quite impossible for us to map the exactly without leaving anything left behind. So this is what it says. If we have a range u and v, and range u and v, and these are equal, then only the function or the codomain would be equal. Okay, now in the another case of surjective mapping, it says that a mapping app such that x maps to y is surjective or onto if the range and codomain are same. That means the range of f is equals to y. Okay, so again this gives the same vibes to that thing. So yes, so these are the mathematical ways of writing these. Yes. Okay, let's see an example to be more clear about it. So we have an example. Okay, let me rub that. A function such that x maps to sine of x is surjective or onto if we consider its domain to be R and codomain to be interval -1 and 1, but not if we take the codomain to be R. What does that mean? So if we have a function such that x maps to sine of x, and we have to say this to be a surjective, then we consider its domain and codomain to be okay. Yes. So we consider the domain to be R, codomain to be interval -1 to 1. But if we take codomain to be R, then it won't be surjective. Now why am I saying this? Let's suppose it's a function, then let's put the values of x. We know for sine is a periodic function, so it will come into the same place after some time. That means it would repeat it. It would be it is a periodic function. So if you start with 0 to 2 pi, the value will increase to 1 and again comes to 0 at pi and again repeat it to the -1 and come to the 0 at 2 pi. So domain, even though can be very large from -infinity to +infinity, the range is going to be inside 1 and -1. So this means that the codomain and domain both are actually perfectly matching. But if we consider the codomain to be R, that means from -infinity to infinity, now this -1 to 1 limit will be smaller than this, so range will be smaller than the codomain, so they won't be equal. That means that won't be a surjective function. Okay. Now if you take x maps to x cube, then if we take a domain and codomain both to be R, that would be perfect for this kind of function. Okay. If it's an x squared function, then again, if x is squared function, then codomain must be from 0 to infinity. Domain can be R. Now these are some basic things about surjective mapping. Now we already discussed that if these two mappings are equal, then we say this to be bijective mapping. Now let's get to the linear transformation.